Consider a satellite adjusting its solar panels in low Earth orbit, or a massive suspension bridge absorbing the weight of rush-hour traffic. These engineering feats function by processing immense amounts of physical data in real time. A single mathematical tool links these disparate achievements. It is designed specifically to coordinate thousands of variables at once. The problem with the physical world is scale. Calculating a single variable is simple, but reality consists of thousands of interacting forces operating simultaneously. This electrical schematic illustrates the challenge. Solving for the currents and voltages in a modern power grid requires managing a massive network of linear equations. At an industrial scale, traditional arithmetic hits a wall. Attempting to solve these interconnected variables line by line is practically impossible. The matrix serves as the structural antidote to this complexity. It strips away the messy overlap and isolates coefficients into a rigid, highly structured grid. By forcing reality into this rigid format, engineers translate physical chaos into a language computers instantly process. Computer graphics offer the most visually direct look at this system in action. Moving, stretching, or rotating a digital object requires the computer to recalculate the coordinates of every single point on that object at the same time. A transformation matrix containing specific trigonometric values acts as an instruction set that multiplies against the object's coordinate data. The immediate result of that multiplication is the physical rotation of the shape in the digital space. This multiplication provides the procedural logic behind all digital movement, 3D rendering, and modern animation. This logic applies just as effectively to physical hardware, specifically in robotics. For a robotic arm to pick up an object, the system must calculate complex kinematics, adjusting angles across multiple 3D joints simultaneously. By chaining rotation matrices together, the robot's computer identifies the exact coordinates needed to position its physical hand. Aerospace engineers utilize these identical matrix calculations to coordinate thrusters and momentum wheels to stabilize satellites in orbit. This shared framework allows computers to map digital instructions directly onto physical coordinates. Matrices are equally vital for things that aren't meant to move at all, like a suspension bridge under the load of gravity. Engineers use the finite element method to slice a massive, continuous physical object into hundreds of tiny calculable pieces. The behavior of every single one of those elements is compiled into a single dataset called a global stiffness matrix. By balancing external forces against the matrix, engineers calculate the resulting physical displacement across the entire structure. This allows designers to mathematically prove a bridge will survive before they pour a single ounce of concrete. Engineering was once limited by dangerous trial and error or weeks of manual arithmetic. Matrix computation replaced those limits with instant, high-precision simulation. Today, this mathematical framework provides the shared language for civil, mechanical, and electrical engineering. This exact same mathematical tool is now serving as the foundational architecture for modern artificial intelligence and machine learning. The connections and weights inside a neural network's layers are simply massive transformation matrices processing data. The matrix remains the mathematical architecture required to turn massive datasets into actionable engineering solutions.